Welcome to part 3 of this video series created for students studying CFD analysis of a quadcopter. In this part, you will learn about the Ansys Fluent Solution Mode workspace. You will also learn how to use basic operations under domain and physics to solve a simple problem from beginning to end. This is the Ansys Fluent Solution Mode that we launched from Ansys Fluent Meshing Mode in the previous part. This is a steady-state simulation, so we will go for steady state. This is a turbulent model. You can find different turbulence models under Models Viscous. There are a lot of turbulence models, but the best choice for most flows is K-omega SST, which is the default model. So press OK. The next step is to define the material. We are going to use air. Double-click on air. There are options for the density. You can try incompressible ideal gas or ideal gas. For this study, change and create and close. The next step is setting up the cell zone conditions. As we discussed in the previous parts, we have 4 domains as rotational zones and 1 domain as the stationary zone. For the enclosure domain, you have to check that if air is inside the domain. Now you have to set up the rotational zones. Before defining these settings, I want to show you how to display the zones inside the solution mode. You can find display mesh in different places, but one of them is here, display mesh. You can deselect or select all the zones. Here, we want to visualize which one is rotor 1. So let's select rotor 1 walls and then display. You can also visualize the global reference frame, which is under reference frame, global, and then display. Okay, rotor 1 is the upper right corner. Now you can go to Ansys Discovery and double check which one is rotor 1. Hide everything and just visualize rotor 1. Now we want to find the axis origin for these rotational zones. For that, go to Measure. Select Measure. Then select the global reference, the center of the rotational zone first. It will give you the correct coordinates from the center of the rotational zones to the global reference. Both have positive signs here. Edit rotor 1 and define frame motion. Use those numbers as the rotation axis origin. We are going to rotate the propellers clockwise, so it's going to be -1 in the z direction. You can define the rotational speed here. Usually, the rotational speeds are in RPM. If you want to change the unit, go to Units Domain, find Angular Velocity, and change it to RPM. The RPM we have chosen for this one is 7,350. Make sure air is inside the domain. Apply and close. Now you have to repeat these setups for the other rotational zones. After defining the cell zone conditions, go to Boundary Conditions, select Enclosure Rotor 1 as shown, and change the type to Interior. That was the side walls of the rotational zones, which shouldn't be a wall. It needs to be interior because it's only rotating. You have to repeat these setups for Rotor 2, Rotor 3, and Rotor 4. You can hide the global frame reference by going to Reference Frames Global, right-click, and then Hide. Now we have 4 rotational zones for which we have defined the center for the rotation, the axis, the RPM, and the sidewalls as interior. The next boundary condition is the outlet for the enclosure. You can use pressure far field for this boundary condition. The Mach number will vary based on the speed of the air inside the enclosure. If we consider a normal breeze for the air, something around 14 to 15 meters per second, the Mach number could be around 0.03. But you can also consider storm conditions by increasing the wind speed inside the enclosure and try different Mach numbers for your study. The next step is to go to Solution Methods and double-check that if the second-order upwind has been selected for most of the equations being solved. The default settings should be okay. If you have any issues with convergence later, you can try high-order term relaxation. You need to define some report definitions to check if your simulation has converged. To do that, you can just select Report Definitions, right-click, and then New. One of the important items for this type of study is the force for the propellers. Select Force Report and, for example, give it a name like Force in Z direction. Then, define the correct direction for the forces, define the walls you want to visualize the forces, and select per zone. I will deselect report files and keep only the plots for visualization. Similarly, create force report definitions for force in X direction as well as force in Y direction. Next, go to Report Definitions, right-click, choose New, then Surface Report and select Area Weighted Average. Rename this as Vel-Far Field. Ensure that velocity is chosen under Field Variable, then select Outlet. Deselect Report File and click OK. The next step is to initialize your simulation. Choose Hybrid Initialization and Initialize. Next, you have to define the number of iterations here. You can try something around 0.5 for the timescale factor and set 1000 iterations for the number of iterations. Then press Calculate. In the next part, I will show you a converged solution and continue with the post-processing of the results.